Now let us start our journey into the cache memory. We'll spend this lecture and next two lectures to understand the underlying concept and its performance characteristics for different types and different operation scenarios. So let's first explore what is a cache memory and what is the motivation to develop that technology. Programming, as a programmer, software programmer, we always look for two features, especially from the memory or the storage: faster access and unlimited capacity. Like, we always read and write from the memory, so of course our program performance depends on how fast our memory or storage can work, and we can how fast we can read, how fast we can write from the storage. And also we need more and more space as much as possible. Like, we are operating on million or billion number of information nowadays, so of course more storage, we need more storage. But these two features, if you recall the characteristics of the memory hierarchy, they are in contradiction already. Like, a faster memory is smaller in size because it's very costly, whereas unlimited capacity is practically the cheapest one but is the slowest one as well. So what can we do? The solution is to create an illusion having a faster speed and larger capacity. So what we are building up as a memory module, from processor perspective, it's issuing address and getting data back or writing data into that address. Simple device. But if we can create an illusion to this model, but within that we can create a specific technique which can give, with some compromise of course, as an infinite capacity, and or not infinite in theoretical sense, but a large amount of capacity versus fast access. Now, two observations from the memory hierarchy. Up in the hierarchy, near to the processor, memory is faster. Like, disk is slower than main memory, is slower than cache, slower than register. And down in the memory hierarchy, memory is slower but large. So what we can do, we can copy the information or relevant part of the program and data which is in context right now into the higher memories from the lower memory. So we keep copies of memories in the different level of hierarchies. So two adjacent levels are involved in this information duplication process, which means a block of information, or it is not a one information at a time. I'll come to that concept as well in later, but it says group of information are copied back and forth from higher to lower and vice versa, and that higher to lower is always happens within the adjacent hierarchies of the memories. It doesn't like, let's say I am copying from the top level hierarchy of the memory, want to copy to the bottommost hierarchy of the memory, but we don't copy them directly onto this larger memory, but what we do, we update the copy into the middle tier of the memory as well, and then to the larger memory. Of course, we can deploy a process where we can parallelly start writing into both the area, but point is that all this content have to be synced in. Now, issue is, since higher memory is smaller, that means not all the information may not fit from the lower level memory related to a program like code or data. Let's say your program and data is occupying all the memory at this lower memory. For example, you cannot copy entire thing to the higher because it is size is much less. Only that means only part of the program and part of the data can be copied back to the higher level of hierarchy. So the unit of information copied from lower level to higher level memory is called a block. So from now on, we will let's review in terms of two-level hierarchy. Like this same like idea can be implemented throughout multi-level of hierarchy as well. So let's focus on the two-level of hierarchies now. So first of all, we don't copy back and forth in terms of one single information. We copy back and forth in terms of multiple words, which is called a block. Okay, the size of block is determined by the cache architect. So it is predetermined, and with some analysis, the like your target application, target marketplace, your architect, hardware architect, especially the cache architect, determined and tell that, okay, this is my size of the block. Upon the processor request information from an address, so processor gives you this whole memory module and requests that, hey, give me information from that address. Let's say we're talking about reading right now. What happens at that point, that information may reside in the upper level of memory, which is then fine. This is called a cache hit. Then my memory system can just give back the data from the high level memory to the processor. Now let's say processor produces an address which is not present in the higher level of memory. Okay, but the corresponding information is present in the lower level of memory. So this situation is called a cache miss, where your information is not available on the higher level of memory, but it is at the lower level of memory. So that means at that point, what you need to do is start copying this block into the higher level of memory before you can get that data back to the processor. So this scenario called is a cache miss, and there is a time delay related to the copying of this data block from lower memory to the higher memory, and that we call it a miss penalty. Okay, so a hit rate or a hit ratio by definition is a fraction of memory access that is found in the high level of memory. Means processor request for that memory, that specific address, is found in the higher memory, and its data is immediately given back to the processor. So that's a hit scenario, and the ratio of that many scenario to the total number of memory access is called a hit rate, and miss rate is just opposite of that, which is 1 minus hit rate. We call it a miss ratio as well. Time to time is a fraction of the memory access not found in the upper level of memory. And as I said, this miss, every miss is associated with a miss penalty. It is a time during which the required memory block is transferred from the lower memory to the higher memory. Let's take an example. Like for a system, upper level memory cycle time is 1 nanosecond, means processor gives a request, after 1 nanosecond your data is ready if the data is present in the higher level of memory. But the miss penalty is 510 nanoseconds. So this is the time it needs to copy the block from the lower level memory to the higher level memory. Now a processor in this system is executing, let's say, 1000 R-type instruction, means we are accessing memory only to fetch the instruction from it. Okay. Now compute the total time of instruction fetch with the hit ratio of 0.8 and 0.4. Let's say hit ratio is 0.8, means 80% time this instruction fetch, corresponding instruction, is present in the higher level memory, and 20% it is missing, so it need to copy that corresponding block into the higher level of memory. Whereas 40% is half of the hit rate. What would be the similar situation? What is the total instruction fetch time? We can approach this problem this way, like 1000 R-type instruction, let's first assume everything is available on the high level of memory. So that means 1000 minus 1 nanosecond, which is about 1000 nanosecond, which is like 1 microsecond, right? 1 microsecond. And then we have a 20% miss rate for the first scenario, right? 0.8, like 0.2 is missed. So 1000 of 0.2 is about 200. So 200 multiplied by 510 is about, let's say 1000. Let's see. Where's my calculator? Here. All right. So for 200 of the instruction, I will incur 510 nanosecond of penalty, which is this, by 1000, which is 102 microsecond, plus 1 microsecond for accessing from the everything from the upper level of memory. This is 103 microsecond. Whereas second scenario, which is like, okay, higher 1000 memory access from the higher level, still chaos 1 nanosecond, so it is still 1 microsecond. But in this case, since my hit ratio is 0.4, that means 0.6 will be a miss. 0.6 minus in multiplied 1000. Since for 600 instruction, it will incur a miss, which is 510 this many nanosecond divided by 1000, 306 microsecond plus 1 microsecond for the normal access from the higher memory to the processor. So 307 microsecond. So you see, with this example, hit rate is very important characteristics of a cache. Even just by like degrading the hit rate by half to half, like it's an 50% of this hit rate is gone, like 0.20, 0.4, we are degrading our performance almost 3 times, right? So it is very, very costly. So that's why our target is to keep the higher hit rate in this system. So 80%, 90%, 95%, as high as possible. That's our goal is. But how is it possible? Why, if we copy a block, and what is the guarantee we will be then successive data access or the instruction access will be from that block? So first you need to understand a block is a consecutive set of data or consecutive set of instruction. Like from memory perspective, everything is data, everything is information. Information is basically either it's a program, machine code, if it is we are talking about the text part of the memory, and it's the data if you are talking about the data part of the memory. But from memory perspective, everything is the information. So we'll use this term information. So a block is a consecutive set of information, and we are kind of lucky that our software program follows 2 types of locality. One is a temporal locality and is a spatial locality. A temporal locality is the property that if we access one information from one point, then it is highly likely soon again we'll access that part or that information. Example, like let's say you are looping through a variable I, okay, looping through a variable I, for loop or while loop. That means inside the loop you are actually accessing the I over and over again, right? Either for you are testing if the I is within certain limit, then you keep on doing the loop, or updating the I, value of the I equals I plus 1, for example. So in either case, within the loop for multiple amount of time, you are keep on accessing the same variable, and you know the variable is practically a memory location. So you are over and over, you will be accessing the same location. That's the temporal locality. If you are accessing one place, it is very likely that you are going to access the same memory address soon. And spatial locality says if you are accessing one location, it is highly likely you are going to access its surrounding location or successive surrounding locations means either like neighborhood location very soon. Okay, that's the spatial locality. Let's say in this example we are accessing 3 arrays with the index over and over, right? In this code, the arrays are again sequential arrangement of elements. Like it's a one after another, it is sequentially arranged per memory address. So that means if you are with this kind of example, which is very common in our program, that we are looping through the array element, then it means we are actually accessing those adjacent memories over the course of the program goes on, right? And your block is nothing but a copy of the adjacent memories. It is not randomly picked up from here and there. The block is we copy as a consecutive areas of the memories together. So that means if your array is falling within that region of the block, you are accessing one point, and then it is highly likely you will be accessed the next neighbor area pretty soon. So that's the property of the software program. One is the temporal locality, where if you are accessing one information or one address, you are pretty likely you are going to access the same memory very soon. And spatial locality says that if you are accessing one memory location, it is pretty soon you are going to access its neighborhood addresses pretty soon. With that, two characteristics of the software program, it is possible to keep your hit rate of the cache memory very high, like 95% or 98%, right? And again, it depends on your application, what type of program you are running and stuff like that. Your market study, that's what the cache architect's involvement is. Job is to specify that what is my block size going to be where so that my hit rate is really high on average in a system. So in this example, it's very much like crude analysis, maybe like couple of numbers here and there, but in this ballpark, in this order. Like, so in the performance evaluation, if you have came across this algorithm study like big O concept, exact number doesn't matter. We want to stay within the ballpark or that power of 10 around that times, right? So with that respect, we can roughly say 3 and 4 is more like an executed 1000 times. Like 3 and 4, even I think 5 is going to be executed 1000. Yeah, line 5 is 1001 time because it's about 1000 time. One time more because last test, when it's going out of the loop, you still need to make that test. So that means these set of instructions are going to be accessed over and over and over again. So if they are within the block, once you copy that block, you are fine. You are within that, and your hit rate is going to be really high. And we are accessing arrays and access 1000 times, and they are also consecutive areas of memories, right? So first two bullet point is covered by your temporal locality. You are accessing one instruction, it is likely that you are going to access that instruction once again very soon. Array C is more like a spatial locality. So we are accessing successive element of the array, so we are kind of covered ourselves with the spatial locality property that will keep my hit rate high. And I is accessed almost like 5001 time. 1, 2, 3, 4, kind of 5, 6 time. It depends on really how the compiler translated this program, but let's say 5 times, 5001 times. This is also temporal locality, and n is also temporal locality. Right? See, it is a constant we are accessing each time we want to access that, want to compare instruction file roughly. But again, remember, it depends on how your compiler translated this code. Like if it's a smart compiler, it will optimize at this part, and of course we can just make it as a one access from the memory. But Again, it's a rough estimate. So what I'm trying to show you here, this, except for this middle bullet point, array C, A, B, C accessed 1000 times, every other part is basically your temporal locality through which our cache hit rate is kept high, whereas this middle point, array C, B, and A access, is basically covered with a spatial locality which keeps the access or hit rate high for the cache memory. So that's all for this lecture 19. If you have question, please ask me in the class or update in the discussion, or just send me email.